So we're just going to go over two type of differential equations where you can use substitution and transformations to change that to something else, so that you can use separation of variable, exact differential equations, or integrating factor. The first type is called homogeneous equations. So it is slightly different from what we have used to classify the differential equations, right? To classify the differential equation, you follow the four categories: the order of the differential equations, the linearity, the with constant coefficient or with non-constant coefficients, and if the differential equation is homogeneous or non-homogeneous. But the homogeneous equation in this context means that somehow you manipulate the differential equations, then you see a ratio of y over x in your equation, then you classify that as a homogeneous equation. Okay, we get to that later. Okay. Now the second equations that you're going to encounter is called the Bernoulli equations. So the Bernoulli equation, we're going to write down the definitions a little bit later, but this is the equations of the form dy dx equal to, plus p of x times y equal to q of x times y to the power n. Okay. So with this form, if you notice, look very similar to the type of differential equations where you can use the integrating factor, right? So the left-hand side, very similar to that type of equations where you can use integrating factor. However, on the right-hand side, you still have q of x times y to the power n. If n is equal to 0, then that is good, and you can use integrating factor. If n is equal to 1, you can use separations of variable. However, in the case of n is greater than or equal to 2, you cannot use any of the technique that we learned so far. So you have to manipulate this Bernoulli equations again to arrive at something that you can use technique like separation of variable, integrating factor, or exact. Now for number 3 and number 4, we're not gonna have time to go over any of 3 or 4. I just want to give you an idea that there exists something like that, and if you encounter, then you need to probably spend time to learn it yourself, right? Of course, in the test, in the homework, I'm not going to ask you number 3, any equation related to number 3 and number 4, just the homogeneous equation and the Bernoulli equations. But number 3 is the equation of the form that dy dx equal to g of ax plus by. So it's in this form. Equation with linear coefficients. So with linear coefficient doesn't mean with constant coefficient, so be careful with that. So usually is of this form: a1x plus b1y plus c1 times dx plus a2x plus b2y plus c2 times dy equal to 0. Right. Again, we're not gonna go over number 3 and number 4. It's just that when you encounter this type of equations, you may want to look up the equations and learn the procedure and the solution process. Okay, so the focus for today, for this lecture, is on the homogeneous equation and the Bernoulli equations. But the general procedure is that you need to be able to identify the type of equations and determine the appropriate substitutions or transformations. Right. So the first step is to identify the type of equation. And determine the appropriate substitutions and transformations process. Right. Now, when you do substitutions and transformations, you rewrite the original equation in terms of new variables. So rewrite the original equations in terms of a new variable. Right. And then you solve the transform equations. Using either separations of variable integrating factor or exact. So either one. And then at the end, when you obtain the solutions of the transform equations, the final solutions or the final conclusions you have to do is that you extract the solution in terms of the original variables. And then the last step is to express the solution in terms of the original variable. Okay, so that's the procedure, right? So look at the differential equation, identify the equations, the type of equation, and determine the appropriate substitution and transformation process. Rewrite the original equation in terms of a new variable. Solve the transform equation using either separation of variables, integrating factor, or exact. And then you express the solutions in terms of the original variables. Okay, so the first type of equation is called homogeneous equations. Now, if the right-hand side of the equations, dy dx equal to f of x comma y, can be expressed as a function of the ratio of y over x alone, then we say this equation is homogeneous. Okay, so that's the definitions for this type of equations where you have to use substitutions and transformations. Okay, so consider the following example: x minus y dx plus x dy equals to 0. So let's say if you can do anything from this, right? Can we use separations of variable? I don't think you can separate that completely. Actually, you can use, let's see, you can use integrating factor, by the way. You can use integrating factor directly from this equations. But let's not just do that. I want to do substitutions. Okay, so it's not going to be exact. So partial n partial x, sorry, partial n partial y is not equal to partial n partial x. So you cannot use exact differential equations. But if you rewrite this in terms of the following differential equations, so x minus y times dx plus x dy equal to 0. Then you have dy dx equal to x minus y over x. So negative. So, or you can write y minus x over x, and this is y over x minus 1. Okay, so the right-hand side of this equation is the function in terms of y over x. Again, you see that if you manipulate this, you can actually turn this into an equation where you can directly use integrating factor. But let's not do that for this exercise. I'm just going to focus on utilizing the substitutions and transformation process. Again, these equations, the right-hand side of these equations can be written as a function of the ratio y over x. Therefore, the equation is classified as homogeneous equation in that sense. Okay, now this is the substitution process. So you let u equal to y over x. Okay, then you find du dx. So this is a fraction. So when you take the derivative of a fraction, you apply quotient rule. Derivative of the top function, which is dy dx, times the bottom function, minus the top function times derivative of the bottom function. So dx is equal to 1. Altogether divided by x squared. Okay. Now you're going to simplify this fractions, right? So from one big fractions, get down to just two smaller fractions. So you have 1 over x simplified with x squared, you have 1 over x times dy dx minus y over x squared. So now du dx is equal to 1 over x times dy dx minus y over x squared. Okay. But you see that dy dx is actually equal to y over x minus 1. Then du dx is equal to 1 over x times y over x minus 1 minus y over x squared. Distribute 1 over x into the parentheses, you have y over x squared minus 1 over x minus y over x squared. Then you simplify these two terms, and you're left with just du dx equal to negative 1 over x. All right. So starting from the given differential equation, you use a substitutions, which is u equal to y over x, and you transform the original differential equations to a new differential equations. And this new differential equation is separable. Anyway, that is, you can move all the thing related to u to one side of the equations, and everything else related to x to the other side. Here you have du equal to negative 1 over x dx, and you integrate both sides of the equations. The integral with respect to u is just u. On the right-hand side, you have negative of ln of absolute value of x plus a constant c. So that's what you get, right? So the transform equation, you solve the solution of the transform equations. Then for the last step, you substitute the original variable back. Since u is equal to y over x, we get that y over x equal to negative ln of absolute value of x plus a constant c, or y is equal to negative x times absolute value of x plus constant c times x. So that's the general solutions to differential equations. Okay. Any questions so far? So let me quickly...
Not yet.
Not yet. Good. Now let me recap what we have so far. So you are given a differential equations. I'm aware that you can just use integrating factor directly. However, the idea for this exercise is to use substitution and transformations. Okay. We turn this differential equations to the differential equation of this form, where the right-hand side of the equations can be written as a function in terms of y over x. If that is the case, you let u equal to y over x. Then you find the derivative du dx. Right? The derivative is, this is a fraction, so that's why you have to use quotient rule. Utilize what you know about dy dx to rewrite the new equation here. Right? This is the transformation process. Right? You transform the original differential equation to a new equation, so this is the transformed equation. And from this transformed differential equation, you use separations of variable to solve the solutions. So this is the general solution of the transformed differential equations. But at the end, you have to substitute the original variables back. Right? That is, u equal to y over x implies that y over x equal to negative ln of absolute value of x plus c, and that's how you find the general solutions to the given differential equation. Okay. Now let me move on to example 2. Again, in example 2, we're going to find the solutions to differential equations. But this one is still going to be the homogeneous equation. This one cannot be solved using any of the technique that we have learned so far. That is, cannot use separations of variable directly. You cannot use integrating factor directly, and you cannot use the exact differential equation directly. Okay. So from here, what you do is that we first rewrite the differential equations as follows. So you have x squared dy equal to negative xy plus y squared plus x squared dx, and therefore dy dx is equal to negative of xy plus y squared plus x squared divided by x squared. Okay. Now you simplify the fractions on the right. You have negative y over x minus y squared over x squared and minus 1. I forgot one thing, sorry. I forgot the negative sign, so there's the negative sign right here. So negative x squared, this is negative as well, so you can, sorry about this. So the two negative cancel out, and so you have this is gone, and you have y over x squared, sorry, y over x, plus y squared over x squared, plus 1, or dy dx equal to y over x plus y over x altogether square plus 1. So the right-hand side of the given differential equation can be written as a function in terms of y over x only. Okay. Now you can use substitutions. So you let u equal to y over x. Then you find du dx. So again, this is a fraction, derivative of the top function, dy dx, multiplied with the bottom function, minus the top functions multiplied with the derivative of the bottom function. So dx is equal to 1. Altogether divided by x squared. You simplify the fractions, you get 1 over x times dy dx minus y over x squared. But dy dx is equal to this expression. Okay. But dy dx is equal to y over x plus y over x altogether square plus 1. We get that du dx equal to 1 over x times y over x plus y over x altogether square plus 1 minus y over x square. So far, so good? Yeah. Now you distribute 1 over x into the parentheses. You get y over x squared plus 1 over x times y over x altogether square plus 1 over x minus y over x squared. So you simplify y over x squared, negative y over x squared. And also at the same time, you substitute y over x as u. So du dx equal to 1 over x times u squared plus 1 over x. Or you take 1 over x as a common factor, you have left with u squared plus 1. Now this equation we just got, this is the transform equations, or transform differential equations. This transform differential equation can be solved using separations of variable. That is, you can move everything related to u to one side of the equations and everything else to the other side. So you get 1 over u squared plus 1 du equal to 1 over x dx, and you integrate both sides of this equation. This is separations of variable. And the antiderivative of 1 over u squared plus 1 is arctangent of u. Again, the formula sheet for this type of integral formula is given in the lecture 0. Right? You can go back to lecture 0 to see the formula. And the antiderivative of 1 over x dx is ln of absolute value of x plus a constant c. Now, this is the solutions to the transform equations. Right? Or to find the solutions to the original differential equation, you substitute u by y over x. Right? Since u is equal to y over x, we get that arctangent of y over x is equal to ln of absolute value of x plus a constant c. And that is the general solutions to the original differential equation. So general solutions. Okay. So I just want to give you 2 examples related to the homogeneous equations again. In a way, you manipulate the given differential equations to the one where the right-hand side of the differential equations can be written as the functions of y over x. Right? When you get that, you let u equal to y over x as a substitution. And then you transform the given differential equations to something else. So at this point, you have transform differential equation, and you can solve for the solutions of the transform differential equation using using the separations of variables, and then you get the answer.